Okay, let's look at step 1, which is glycolysis. Notice we're starting out with C6H12O6, and we're going to be going through several biochemical steps to break it down into 2 3-carbon products. Now, yes, we have hydrogens and oxygens, but we're really going to just follow the carbons, but we will discuss what's happening to the hydrogens and later on what's happening to the oxygens. But what we're really trying to do is we're trying to take glucose and break it down into 2 products, which also have carbon, hydrogen, and oxygen, called pyruvate. Now, in order to go from this 6-carbon product to these 2 3-carbon products and get some other things out of it and to proceed this direction, we actually have to start out with ATP to cause this to happen. So we literally start out with 2 ATP. We end up actually making 4 ATP, but because we pay back the 2 that got it started, we end up with a net gain of 2 ATP, as you see here. So what are we getting from this? Well, we're breaking this down into our 2 3-carbon products, because 3 and 3 make 6. We got some ATP out of it. We had got 4 out of it, but we had to pay back the 2 that caused it to work. All right, we got our pyruvate, which will be used for our next step. But what we really got out of it was we pulled some of these hydrogens out because we converted a product called NAD plus to NADH. Okay, so we actually, since a hydrogen is made up of a proton and an electron, we needed the electron to get rid of that. So that left a proton over. Then the other hydrogen we see just gets added onto the end. So we needed 2 hydrogens to convert this NAD plus to NADH. But in this first step, what we actually get is 2 NADHs. Now, we're going to take those hydrogens from the NADHs. We're going to use them in the last step that we talked about earlier. Now, pyruvate is often referred to as a pivotal metabolite. And what that actually means is that it can either stay out in the cytoplasm, because that's where glycolysis takes place, or it can go into the mitochondria in step 2, the transition reaction. What determines whether it does it or not is, do I have enough oxygen being used in the mitochondria to open everything up so the pyruvate can go into it? Now, I'll show you what I mean by that in more detail later, but it really is dependent on the amount of oxygen, and do I have the oxygen, enough oxygen to maintain whatever my activity level is. If we have enough oxygen to continue on with the process of cellular respiration, then the pyruvate is going to transition into the mitochondria, go through the 2 membranes, and while it's doing that, it's actually going to lose some carbon dioxide. So this 3-carbon product will lose one of its carbon dioxides and oxygen. So since there's 2 of these going through that step, then we're going to lose 2 carbon dioxides at that step. Well, if I have a 3-carbon product named pyruvic acid and I lose a carbon in the form of carbon dioxide, now I have a 2-carbon product, and this 2-carbon product is actually called acetyl. Now remember, this is actually happening twice, because when we started out with a glucose molecule. We split it into 2 of these. Each of these, if there's enough oxygen to power the cycle, if there's enough oxygen to run the last step, then both of these pyruvate acid molecules go into the mitochondria, each of them losing a carbon dioxide. So then we are going to have 2 acetyl products. Okay, now we are at the next step where our 2-carbon product called acetyl, which is now gone through both of the membranes of the mitochondria and actually lost the carbon dioxide. And so we went from the 3-carbon pyruvate to the 2-carbon acetyl. And once it's inside, there's an enzyme, a coenzyme called coenzyme A, that actually attaches to it. And what do enzymes do? Well, they either put stuff together, break stuff apart, or rearrange stuff. So this coenzyme A actually grabs the acetyl. So now we call it acetyl coenzyme A. It joins it with it's actually called oxaloacetate, a 4-carbon product that's already inside the matrix, the middle of the mitochondria, it's always being recycled, used over and over and over. So I took this 2-carbon product that came in from my glucose. I am now hooking it up with a 4-carbon product, and now this 4-carbon product, then because I add a 4-carbon to a 2-carbon, the enzyme does that for me, then I get a 6-carbon product called citrate. And that's why this is called the citric acid cycle, because of this product that is formed. Now, again, we're not going to worry about the names of all the biochemical steps. There are plenty of things that we can look at if you're interested in that, but I'm more interested in you understanding what's actually going on here. So again, notice we're following the carbon, so each of the little beads here represent a carbon. So I've got a 2-carbon plus a 4-carbon, gives me a 6-carbon. And now I'm going to remove hydrogens, because remember, when we turn NAD plus into NADH, it's actually taken 2 hydrogens to do that. So we took our hydrogens, we converted NAD plus to NADH, so now we can take the hydrogens to the last step. And that's one thing that all three early steps have in common, is that we're always pulling hydrogens out to take the hydrogens to the last step, which is in the electron transport chain. Now, something else that happens here is when we pull those hydrogens out, we're also getting rid of another carbon dioxide. So that means that, even though we're just showing the carbons here, we know there's hydrogens and oxygens, so we just removed 2 more oxygens and a carbon. Well, if I had a 6-carbon product, which is what citrate is, and I remove a carbon dioxide from it, now I've got a 5-carbon product. Okay, so notice now in this sequence of events, I'm taking a 5-carbon product. I'm also converting more NAD plus to NADH. I'm doing an oxidation reaction. So I am taking hydrogens out of here. So when I remove hydrogens, it's an oxidation. If I add hydrogens to something, it's actually a reduction equation. So that's why we say oxidation reduction reactions. But this is the oxidative part. We'll see the reducing part later. Okay, so I'm pulling hydrogens out of here. I've pulled a carbon dioxide out of here. I'm reducing, I'm oxidizing NAD plus to NADH. Okay, notice then I pull out another carbon dioxide. So I went from a 5-carbon back to a 4-carbon product. Now, notice that I started out with a 4-carbon product. I am back to a 4-carbon product. I came in with 2 carbons, and now I've taken out 2 carbons. And these carbons that are on the carbon dioxide that we're actually going to be exhaling always came in from the glucose that we ate, or we can also break down fatty acids the same way and amino acids if we had to. But the carbons here came from the glucose, so these 2 carbons that we're getting rid of were always these 2. They've actually done experiments where they radiated the glucose, and then they tested the exhaled air, and it was always radiated carbon dioxide. So this 4-carbon product here, it's a different biochemical product than these, but the carbons are the same. They are the same 4 carbons that keep being recycled. So when we keep going through our Krebs cycle, our cycle, and of course we know we're going to go through this twice because we started out with glucose, which broke down into 2 pyruvate, which then both got converted into 2 acetyl. So here's what's happening with one of the acetyl groups. Okay, now back to this. So we're at this 4-carbon. We've lost our carbon dioxides. We pulled hydrogen out to form NADH. We've pulled hydrogen out to form NADH. Now we're actually going to, and really what we're doing at this point, we're actually converting something called GTP to ATP. But for our sake, it's just good to know that we actually form a little bit of ATP at this point. We form 1 ATP per turn. But since we know there are 2 turns, then we're going to get 2 ATP from this 3rd step in the process. Okay, but here we get something that is only found in the Krebs cycle. We actually pull some more hydrogens out, and we convert FAD to FADH2, which is easy to see. Obviously to go from FAD to FADH2, I had to get 2 hydrogens. So those hydrogens were part of these molecules. All right, and then finally, as we're converting back to this oxaloacetate so we can do the process again, we pull again, some more hydrogens out of it to convert the NAD plus to NADH. Now, so I know this is probably a little overwhelming if this is the first time you're seeing this, but again, the big picture is I'm taking products that are the breakdown product of glucose. I am losing carbon dioxides in this process, and I'm also pulling hydrogens out of this breakdown product because it's really the hydrogens that I'm interested in that I'm going to use later, and in the meantime I get the benefit of a little bit of ATP that's produced at this point in the reaction. So finally then, what are we going to do with those hydrogens? But before we talk about that, let's just get a countdown. So I have, for each acetyl, and remember I'm always going to have 2 acetyl per original glucose molecule, but in one term for one acetyl, I'm going to always get 1, 2, 3 NADHs and 1 FADH2. So that meant if there were 2 terms, that means I would get 6 NADHs and 2 FADH2s. I get 1 ATP per turn. So for 2 turns, I would get 2 ATP out of this.